the maximum anisotropy, and it says when you increase that anisotropy, rho is like 1 over that anisotropy, and it says that your inversibility goes to 0 with 1 over the anisotropy to the n over 2. Now the thing is, and that's what I don't have time, is we've looked at could you do different maps in here, and instead of powers of 1 over the anisotropy, could you get a negative exponential? And you actually get. So you can get very fast convergence in terms of how anisotropic your materials become, and which is very important for actually manufacturing these. And that's, again, I want to just point out, there are a lot of sort of, I think, open problems, it ties in very much to numerical analysts look all the time at these things, they call perfectly matched layers. Basically what you do in perfectly matched layers is you want to solve a problem in an infinite domain, but you restrict it to a finite domain. You have an infinite domain where you have a boundary condition that's a radiation condition at infinity. You put a 0 condition at a finite domain. Basically what you're doing is you're cloaking infinity. And you're making 0 Dirichlet data looking like the radiation boundary condition. You're making some transformational optics in between. And so this actually, the optimization that we've looked at is very related to perfectly matched layers. I'll stop here. Thank you very much for inviting me.
Thank you very much for time for questions. So I have a question about the coefficient C.
Yeah.
So on which parameter is depend on? We should depend on something.
So it does not depend on A. So the main thing is it does not depend on A. It actually is a universal constant. It's universal. It doesn't, because I'm doing this, if I were to change if I were to take different domains out here, it would depend on the domain. If I were to take different mappings, I took the 2 balls, I took the 2 concentric things, right, B2 and B1. And so I have a particular mapping F here. So this coefficient would depend on the geometry. But I have a particular geometry, a particular F. And so the only parameter I really have in here is rho. And that's the only thing it depends on. It's independent of rho, right? Because, and it doesn't depend on the only thing it could depend on. Now, out here I said I wanted to have 1.
Do we depend on the geometry of the pattern?
It depends on the geometry of B2. So for different B2s, you could have.
For B2
Well, it's a constant for B2. But it's a universal constant because it doesn't. I have 1 here. If you said you wanted to make it look not like 1, but you had some other medium. I mean, when you do sort of optical illusions, you could say, I want to make it look like something else, not necessarily 1. And so then it would depend on what else you wanted to make it look like. But in this case here, I have a very special situation, and I showed you why this very special situation is really the generic case. And I have 1 here, I have B2 here, and the thing it is independent of is what you're wanting to hide. That's the important fact. It's completely independent of that. And everything else, if I change B2, if I change the 1 that I have here, it would depend on that. But it's independent of A. And that's really the only parameter that's left is A, because all the other parameters I've taken out.
And another question about the Planck function. So if you say there is no more isotropic, can you say anything more about the function itself?
Well, this one here, the globe.
Yeah.
Well, I mean, the formula for this particular, the formula is here.
Yeah.
And so it's given in terms of its, this one here is actually, it's very funny, so I'll tell you a little story. This particular function was in this paper that Pendry, Schurig, and Smith wrote that got them on the front page of the Science Times. And they were doing a lot of work. Now there was a paper that had been published 3 years before by Greenleaf, Lassus, and Luhmann in a paper, some physiological paper. And the title of the paper was particular conductivity distributions that are invisible to impedance tomography. Well, that doesn't sound as sexy as you can cloak things, and so no one really noticed that same transformation had been used. But I mean, there's nothing special about this transformation. It's just by this transformation you can calculate everything. And so this is what it looks like. I mean, it tells you exactly what the eigenvalues are in the normal direction. This is the normal direction. It tells you what this slope is actually. It's a diagonal matrix where this is the where this thing here is actually the radial. Where this is a radial direction, this is normal direction. And you calculate exactly. This is the normal direction eigenvalue. This is the radial direction eigenvalue, and you have a very specific formula. But there's an interesting question. Exactly to bring down this constant, you could say I could take other mapping, and so you could look how does this constant depend on the mapping. Now we have proven in the circular context that the best thing you can do is take a radial map in terms of the anisotropy. Take a radial.
How difficulty that's
Well, so that's what engineers keep telling me. I mean, it's hard to construct materials. So this is a real, I mean, I think there is terribly interesting mathematics here. And I'm not going to tell you that we're going to make things invisible. But what we're investigating is, in what sense is it possible with the Maxwell's equations to do it? What kind of coefficients do you need? And we can sort of say, well, this is what you can do if you can construct these kinds of coefficients. And engineers, of course, have the limitations, what kind of coefficients can they construct. And they will tell you that it is very hard to construct a material where the aspect ratio between conductivity in one direction and conductivity in the other direction is more important than a factor of 10. So basically this tells you that lambda max over lambda min should be less than 10, otherwise they're going to have trouble. And they are, I mean, there are engineers, there are lots of engineering groups that are trying to construct these flows in both 2 and 3 dimensions. So I mean, that's going to be the real test of whether this is going to be practically interesting, is can it construct. And we are just there saying, well, we can show, for instance, that it's easier to do in 3 dimensions, but of course, engineering-wise, it's harder to construct in 3 dimensions. And we can sort of say, well, these are the things that are possible. What can you do and what can't you do? So we are having some sort of interaction. But the real art problem, which will determine whether this becomes successful or not, is can you construct these things? And let me put it this way, there's a lot of energy going into it. Because you can imagine there are lots of interest in trying to make things. I mean, I want to find things, but there are other people who want to make them invisible. Yes?
Yeah. How does your theory relate to the theory of the black hole in physics? The theory of black hole.
Black holes, I don't think there's any... yeah, I mean...
Yeah, they said that one cannot observe the black hole.
Yes, and so you could say the same thing. I mean, there's certainly, so let me make the analogy, I just make the analogy to what's called perfectly matched layers, where people are trying to solve an equation in infinite space. And the way where they have some radiation condition at infinity. And then they say, well, we cannot solve with a finite element solution in infinite space, so they truncate to a finite space. But if they truncate to a finite space, and say now it's 0 boundary conditions here, then the rate at which this converges gets determined by how fast your solution goes to 0. Well, the Helmholtz equation in 2 dimensions goes to 0 like 1 over the square root of r, and that's what the fundamental solution, that's what the Henkel function looks like. So it's very slow. You have to take an enormously big domain. So then they come up with a say, well, maybe we can construct a layer around the surface so that we take the equation out in complex plane. And out in complex plane, the Henkel function decreases exponentially. And so now they suddenly get exponential convergence by doing the right kind of layers. And it looks a lot like a cloak layer. And so what I think of PML is actually cloaking infinity. And we're trying to investigate exactly the relation between cloaks and PMLs. And so if there's any connection to what you're just bringing up with black holes, I think it would be in that kind. But I'm sure they are connected.
Last question.
The last slide, I saw you have some kind of error about it, and then you say that the last slide. Yeah.
Yeah, so we have this error bound where it says.
Yes. How about the geometry? Do you point the object had to be a sphere or a circle or?
Well, so what I say is this constant here will depend on that you're in this geometry. And now it says you put anything inside, and your Dirichlet to Neumann data map out here, and the Dirichlet to Neumann data map of 1 are this far apart, independent of what you put inside. It just depends on my rho. The rho is sort of a fictitious parameter. It's a parameter that I used over here to define my flow by this mapping. And I then came back and said I could really look at it over here in terms of the ratio between the maximal and the minimum value, because that's really what's relevant. I have something that becomes very degenerate here, and I want to find out how small is this when it becomes very degenerate. And I said rho was sort of like, rho became like lambda max over lambda min to the -1/2. And so therefore you have this becomes like n/2, and so this becomes, it tells you exactly what happens here in terms of the material parameters. Because you can forget about this. This is sort of not really a physical situation. It's just how I construct my flow. I take the one over here and I map it. And then the wonderful thing is I have estimates that lets me prove this estimate of what is the effect of a small inhomogeneity independent of what's inside. See, because here it's not small, and I have something inside, so I cannot make estimates independent of what's inside. But over here, I can make independent estimates of what's inside because I've made it small. And you could say, well, that's a trick. I mean, it can't be independent of what's inside, but that's a beautiful thing, is it's independent of what's inside. And that actually depends on the fact that you've scaled in all directions, because if I had scaled, if I had a small set like this, if this was my rho and this was 1, then this constant here would not be independent of what's inside. It's because the set is equally small in all directions. Because see, this set here, when rho goes to 0, shrinks to a curve. And in the rho limit, a curve has capacitance. And so it would support something that is different from the 1. But in this case here, this shrinks to a set. And a set is a removable, a point is a removable singularity, has no capacitance. And so that's why it's so wonderful. And so that's why the fact that you are using something that is equally small in all directions is very important in terms of your map. And that's why we used a radial map, or why Hendry, Schurg, and Smith, and Böhmer, and Lasses, Lasses and Ullmann used that kind of sort of trying to, it's something I looked at for a long time, and therefore maybe I'm not always aware of sort of difficult the first time you